Ready? Okay, welcome to Urbana, Illinois, Power and Energy Systems Seminar. We have a speaker today from Indiana, Aaron Anderson, who's going to talk about some interesting new machines and drives, high frequency air core, forget the iron. And Aaron, go ahead.
So today I'm mostly presenting what the work of most of the Huron group for much of the past year. We are working on a NASA grant, and we have an annual review coming up. And so this is a sort of preparation for that. So if any of you have comments at the end or questions throughout, that's totally fine, of how to improve this and make it clearer for our actual annual review for this grant, that would be appreciated. So there's a whole lot of work that the Huron group has done over the past year. There's no way I can talk about everything in detail, but I'm going to try to make it through much of the stuff. I know many of the people here are already quite familiar with our motor, but I'm going to describe it briefly. It's supposed to be rated for 1 megawatt, 96% efficiency operation, and it's a permanent magnet motor and what we call inside out, meaning the rotor, the part that spins, is on the outside and the stator is on the inside. And much of the work in the past year has been working on building and testing components of it. So to give an overview, working from the inside of the motor, we have an aluminum heatsink. That's how we pull the heat out. An iron yoke, pretty thin in this case. Coils that are air wound, or air gap wound coils. So these are coils that directly face the air gap. A Halbach array of magnets, titanium retaining shell, and a carbon fiber retaining ring. So a big theme, in my view, of this year's work is test, adjust the design, and repeat that process. There's been a lot of testing, a lot of design tweaks, to get to a place where in the next couple months we should have a finished prototype ready to test all the way. So the first category is the rotor construction. So towards the end of just about a year ago, we sent this to a company. We sent a slightly scaled down model to a company to spin up to full speed, and we got a lot of information from that test. And based on that, we saw, looking at the vibrational characteristics, there were some concerns there about the amount of vibration we were getting. And so the first adjustment after this test was changing the thickness of the end plate. And by changing that, we changed the an aspect ratio, essentially, of the moment of inertia along different axes that helps reduce the rotor dynamic or vibrational issues. And then continuing with manufacturing this rotor, this is showing the carbon fiber outside of the titanium shell. This is most of the way manufactured. And near the end of, as many of the parts were finishing manufacturing, we realized that there's a spot on the fan assembly where the metal is very thin and there'd be too high of a stress concentration. And so adjusted the thickness of that to mitigate the things. So this was an instance where we were able to, instead of doing testing, doing simulation and analysis, determine that this was not going to be a safe design. And then the fan was manufactured, and much of the rotor, the parts that we built in-house, were assembled and packed up to ship for magnet manufacturing and installation. And that is a slow process. As of a few days ago, the most recent info we have, the company that's doing that has made these magnet packs that are sets of magnets glued together and installed about 45% of the sections of the magnets. And so work is progressing with that, assembling the rotor and getting the magnets built there. So the next category to talk about is cooling and airflow testing. So in the same test that we did about a year ago on an off-site location, one of the results there was it looked like we were getting insufficient airflow to cool the motor, and that's really concerning. And so we built a test setup on campus to use the same slightly scaled down motor and to drive it with a different motor up to partial speed, and added instrumentation there with thermocouples and pitot tubes to measure the pressures. And that gave us a better idea of how much airflow was getting through and how much windage losses, and so the temperature rise associated with that. And so using this information and looking at some of the results, we were able to extrapolate what temperature rise, and based on that, decided to, a lot of charts here, decided to increase the thickness of the air gap, which would allow increased airflow with the same pressure drop from the same fan. The fan didn't change design. And so by increasing the air gap, increase airflow and decrease the peak temperature. And that should also lower the windage loss, so reduce the amount of heat that needs to be removed. And this work was also supported by some CFD, some computational fluid dynamics, to give it a good understanding of how that airflow is working. And the next category is stator construction. The stator construction has happened mostly here on campus, and there are a variety of different categories within that. First category is winding manufacturing. It's a video. Kevin, can you try clicking to see if we can get the video to play? If not, we can move on. Yeah. Seems like that's not going to work. So I'll just describe what this was showing. There, we did the process for the windings. So these are the coils that carry the current to create the electromagnetic field, the magnetic field, and these were wound by hand here on campus. Several of the people in this room did a lot of work on those. And along the way with those, there were various issues that we found. Some things we changed were just to improve efficiency and make it go faster. Other issues were integration with the rest of the motor. And so in order to connect this, we have to have leads that come outside of the motor. And one issue we faced and fixed was that those leads in an earlier, initially, were bending out in this direction. And that, in fact, was going to hit the rotor. And that's no good. If your rotor is scraping off your leads, your motor will not run for very many minutes before it stops working entirely. And so we redesigned the fixture just slightly to allow the leads to come straight out the end, and that prevents interference with the rotor. Another issue was the wire stripping process and the soldering process. So the wire we're using consists of 660 individual little strands, each of which is independently insulated, and then their bundle and insulation as well. But in order to connect those, to solder those to another connection, we have to remove that insulation. And the process that we had initially was not effective or consistent with removing all of that insulation. So we adopted a new process using molten sodium hydroxide instead of an aqueous sodium hydroxide solution. And that allowed for more consistent soldering. And here we are showing, this is the pot in which there's the molten sodium hydroxide, which removes the insulation. And this is using a felt polishing wheel to remove the bundle insulation. And so these were significant improvements. Now talking about winding qualification, how do we know that the windings we build actually work? They do what they're supposed to do, and the insulation is sufficient is a big question. So one part of that has been accelerated aging testing. And so with these accelerated aging testing, that's applying higher frequency power to the coils at a higher temperature. And by doing those two things, we can simulate really rapid aging of the insulation. At the end of the process of running through this test, the idea is to get a good idea of if the insulation will actually last an acceptable lifetime. So it's a pretty big setup to do this, including an oven, a power supply, switches, a function generator to create this these high frequency pulses, and various equipment to monitor the voltage and current going through them and maintain appropriate temperatures and safety margins and all. And so with that, one of the things to look at, a major thing to look at, is the current and voltage in the winding. When a voltage impulse is applied, it's expected there will be ringing, and looking at the frequency of that ringing indicates partially the health of the insulation. As the insulation breaks down, you're going to have lower resistance between turns and between individual strands. And so by looking at the waveform there, you can begin to get an idea of the aging. Another part of the winding qualification is partial discharge inception voltage measurement of the stator coils. And so PDIV is how we abbreviate that. That indicates when you have an insulation material, if you have wires next to each other, if there are defects or bubbles in air bubbles within that insulation, you can get voltage discharge or tiny little electric arcs between within the insulation. So it's not a full discharge from one conductor to the next. It's small ones within the insulation. And this is not an immediate huge problem during operation. It's not going to immediately destroy it, but it is a lifetime concern, because each time there is this partial discharge, it's going to damage and wear away the more of the insulation. And so over time, as you have partial discharge, it will eventually typically cause a dead short, which is not where we want to go. And so the significant part of our testing has been PDIV Inception Testing, which is where you increase the voltage progressively until you start to observe partial discharge. And we've used that to qualify the various coils. And so this is a little bit of a schematic of the setup. So by using a variac and a potential transformer, we're able to adjust the voltage and step that up to a higher voltage, and then sense the current going in. And here is what the actual setup looks like. Point out also that there's a vacuum chamber. So the insulation tends to be less effective at partially reduced pressures. And so by running it in a vacuum, we can simulate altitude, airplane altitude. And so that allows one more set of control for understanding the qualification of the insulation. And we can see here the test setup validation. And so by using just wire rather than our coils, we can choose to have wire that we know is really well insulated or poorly insulated and have control there to validate that the setup gives good results. And in this oscilloscope plot, you can see these high spikes. Those are indicating where partial discharge occurs. And there'll be another plot later on where we can see a couple different ones comparing partial discharge and showing a region with and without partial discharge. So this is showing a test coil fixture. And so the way this works is that this metal plate is connected to ground and high voltages are applied to these coils. either from a coil to the plate or between two coils. And that allows us to test the insulation on different sides of those coils, say the side facing ground or the side facing another coil. And so the goal here is to measure the partial discharge inception voltage before and after this accelerated aging process. And so when initially doing the test, we found breakdown voltage below the level that we really were targeting at about 1 to 1.7 kV RMS. And so that was concerningly small, and this was full breakdown, not just partial discharge. So basically destroy the coils. And so that was concerning, and so led to, oh yeah, and here you can see the spots where the breakdown occurred. You can see the burnt spots. It's going to be hard to see on these ones because they're small, but here's a closer up picture. So that's concerning, and so in order to mitigate that issue, added an additional thicker layer of the resin between, or so the epoxy between the coils and the ground plate. And so by adding that additional epoxy that is thermally or electrically very insulating, we were able to reduce that. And we can see here that this is at 1.12 kV, so already above where the other one had full breakdown. And there are few partial discharge events here. And then at 2.5 kV, you can see a lot more partial discharge events. And so that indicated that adding these extra 0.010 of an inch of resin was sufficient to prevent the voltage breakdown. And so this is showing average, average across multiple trials was about 1.1 kV for partial discharge inception voltage, which is above the operating point, and partial discharge is not catastrophic failure. So it's okay to occasionally have some partial discharge. And also demonstrated that the partial discharge inception voltage decreased at increasing temperatures, which is to be expected. But it's important to understand because the operating temperature of our machine is expected to be quite a bit higher than room temperature at 200 C, or just above 200 C. And so by, again, talking about the aging test that was motivation for a lot of this testing, it's going to be within an oven to heat it up. And this is a proposed improvement on that aging setup, which hasn't yet been set up and used. But by improving the setup, hopefully going forward, we'll be able to get additional information and a better understanding of how the coils will age, and not just, right now we're fairly confident. We're confident that they're sufficient for a short-term operation, sufficient for initial testing. And then this is showing additional setup for testing by adding the ceramic-filled resin and comparing that to aluminum-filled resin for that additional 0.010 of an inch of insulation. And here we can see the green line is the lowest. That's the aluminum-filled resin. The blue line is the bare aluminum block. And so by adding aluminum-filled resin, that was very similar to, but slightly worse than just connected straight to the block. But adding the ceramic-filled resin, which is a much better electrical insulator, that actually improved the PDIV, increased the PDIV. Another validation, or another test that we did was to understand if the coils themselves would be able to take the torque that they were generating, because its motor point is that it generates torque, and we want to be sure that they would not either get damaged by the mechanical torque application or shear off from the yoke that's underneath. And so we did this shear stress test where there's a sample, a small piece of the winding within that fixture, and then this is a load cell. And so we were able to press down on that and measure the exact, or pretty exact force being applied, and then by that understand the shear strength of the material. And so what we needed was 9.24 pounds of force. Fortunately, the machine's measured in pounds, so we needed about 9 pounds of force to be able to withstand the forces that would be experienced within the machine. And we found when testing through the middle of one turn, so each winding has 3 turns stacked on top of each other, and when testing through the middle of one turn for the force application, we were getting forces above 200 pounds force, which is well above the minimum required. We found even higher strength between the turns, and that is presumably because the resin doesn't perfectly penetrate within the wire within one turn, but between turns there's consistently a really good layer of resin, and the resin is stronger than the copper wire. And then the next test was between the coil and a piece of metal, the laminations, and with that, using the ceramic filled resin, 2 of 3 were very strong. The third one was significantly weaker, and with the aluminum filled resin, fairly similar results. But these results, and here we can see how they broke off. However, after determining that we needed to add that extra 0.010 of an inch of resin to prevent the voltage breakdown, repeated the test and found more consistent of results, or results that were more consistently well above the minimum force required. Still some significant variation, and I think that's largely due to the setup, and it's really hard to very consistently apply the resin at the specified thickness and make sure that all of the materials are clean to get a really good bond beforehand. And so nonetheless, with the additional 0.010 of an inch of resin, we're confident that that is sufficiently strong. So the next category is assembly of the stator. So a year ago, at the last annual review, the heat sink was just about completed. And these are stacked up pieces that were wire EDM'd, so very accurately machined, and that was joined together. The ground cylinder is the piece that goes inside of that, and the bearing has the bearing housings. That was assembled. And then we received the stator yoke. That's the cobalt iron that is part of the magnetic circuit. That's an active part of the machine. Unfortunately, with this, as it's a stack of lamination, so thin layers that all stacked and glued together, and that stacking was not done as accurately as we would have liked, and so there was significant offset between layers. We can see about 37 thousandths of an inch on the outside diameter variation, which is may not seem like a whole lot to us, but that's getting pretty close to the total thickness of the original air gap. And so that's very concerning, and we had to find ways to work around that. Luckily, we had determined we needed to increase the size of the air gap to get enough airflow, and so that helped somewhat mitigate this. And in addition, we slightly increased the diameter of the rotor to help make up for that. And so also, these were not consistent, and so to cancel out the variation in shape and the offsets between the layers, a layer of aluminum-filled resin was applied to the inside diameter, and then machined off until to provide a clean cylinder shape until it just barely showed the laminations, and that allowed a good surface for joining onto the heatsink, which goes just inside of that. And so joining the heatsink and the yoke was a shrink fit. So that's where the inside part, the heatsink, was put in liquid nitrogen, where it sat for several hours until that was at the temperature of the liquid nitrogen. And as it gets cold, it contracts a little bit. And then the yoke was heated up from the outside and warmed up. And as it warms up, it expands. And so then they were able to just slide onto each other very easily. And so the heat shrink went well, and we were able to join the two parts. And then once they neutralized to be the same temperature as each other, they are fit very well together and will never come apart. So here's showing once they're assembled, and we can see the windings are going to attach there. But in order to mitigate the fact that on the outside as well, it was not a consistent or smooth surface, the ceramic-filled resin was applied to the outside. This is important also for the electrical insulation properties. And then a thin layer was applied, and a layer just thick enough to fill in the gaps was applied, and then an additional 5/1000ths of an inch was applied to the outside for the electrical insulation. So this is the finished yoke with that ceramic-filled resin applied. The next step in the process of the stator assembly is to put on the windings. And so to do that, we did a dry fit where all of the windings were assembled onto another cylinder of the same size without any glue and not the final cylinder. And this is just to test to see if it fits and to determine what issues there would be along the way. It was a very good thing that we did this dry fit before trying to do it with the glue, because we found that the gaps between the different coils were inconsistent. Some of them were pressed up against each other really hard and had to be pushed in hard, and there were small gaps in other places, and that was not going to be effective and not going to work. And so in order to fix that, we realized that the angle between, or the space between the two sides of each coil was slightly too close together. And so they needed to be stretched apart slightly. And so a set of plastic or Teflon pieces was then used to stretch out those pieces. And here we can see the pieces applied that are doing the stretching and the process of that. And it's a little bit concerning when you have your resin that makes it very stiff, and if you stretch that, there could be risk of damaging the insulation between the within the stator. And so the electrical resistance of the whole coil was measured, and so a change in that would indicate either things got shorted out differently, or some of the conductors may have broken. So what we found was, while in the fixture stretching, there was some increase in resistance, somewhere between 0.4 and 1.8% increase in resistance. But once they were removed, once the fixtures were removed, there was somewhere between 0.15 and 0.7% increase in the resistance, which is small enough that we were not too concerned about the effective stretching. Of course, if we were going to do it again, we'd rather not need to stretch, but at that point, it was better to stretch out the coils than to start over. And so the next step then is to begin to attach the coils to the stator. And so started with another practice to make sure that once they were stretched, they fit better, and in fact they did. And then actually glued them in place onto the stator, onto the yoke. After doing that, tested the insulation between each coil and the ground cylinder, and found that that insulation, the current that was allowed through with this Megger test, was small enough that indicated we had sufficient insulation. And then repeated the process with the B phase and C phase, doing a dry fit and then a final glue fit. Slow to advance the slides. Okay. And doing the electrical testing for each set. So here is a picture showing different sides of the completed stator with all of the windings attached. And the results after testing the insulation of all of them were very high resistance, indicating that the insulation was succeeding, was doing what we needed to. And these are a couple close-up pictures. This is on the fan side, so the outlet side of there. And this, you can see, this is the side with all of the leads coming out. And this is where the air is inlet. And you can see a lot of the wire is beginning to block the flow, or where the air needs to flow. You can also see there are a whole lot of leads coming out, sort of making a little bit of a tangled mess. And so those are two issues that I'll address in just a minute. We also sprayed on a 1 mil thick or 1/1000th of an inch spray insulation to coat the outside. That's to provide just a little more electrical insulation and a little strength to resist if somewhere along the way something bumps it. We want to have a little bit of scrape protection. So first, next to deal with the tangle of leads coming out, designed a plastic ring that will hold all of those wires in place and keep them nice and organized. And so built and installed that, and that provides quite a bit more order and consistency with where those are. And then to mitigate blocking the airflow on the inlet side, a fairly simple solution was tie string onto the parts that were blocking it the most and pull those up and open up a little bit more flow. Not a perfect solution, but it was the solution available to us. Close up of that. And so this is final fan side of the rotor. So this is the outlet side. And next, talking about the qualification, how we made sure that mechanically and electrically, I've already discussed electrically somewhat, this was the right size. So measured the radius, the outside radius of the stator, and found that it was within an acceptable tolerance of the nominal value. And based on that, it looks like the average air gap will be about 1.7 millimeters, which is acceptable. It's about where we want it. Again, retested the insulation and found that, again, acceptable and was high enough for what we were looking for. However, there's another set of electrical testing. We haven't done full testing up to the full voltage because there's concern once you pass the breakdown voltage, the coil will be permanently destroyed. And so we tested it to partial voltage and it worked fine at that level. Our plan is to do some initial tests, and then after the initial tests, electrically test it up to full voltage and do more complete tests to avoid the risk of destroying the machine before we have time to test it. And leakage current also very low, and impedance measurements as well were within the tolerances, within the ranges that we had set. So going forward, we want to, the plan is to test this motor, and we want to test it as thoroughly as we can and get as much information out of it as we can. Unfortunately, as I said, the magnets are taking a very long time to get mounted into the rotor. And so in the meantime, we've begun making an alternate rotor, which we can build, is not nearly as good as the final one will be, but we are working on building that here on campus. And that should allow us to get some initial tests and to get back EMF reading, hopefully within the next couple weeks. And so this is built out of Bakelite and PVC with magnets on the outside. And looking at this, the back EMF of the final rotor with the full-size magnets should be about 600 volts RMS phase to phase. And with this test rotor, a maximum of about 22 volts. And so this is a much, much lower power, but 22 volts is still enough that we can certainly measure it with equipment that we have on campus, and there shouldn't be excessive noise or anything in the measurements. So that we hope to give initial results and show some of how it works. But for final testing, we want to go full power, of course. And so the plan is to go to UTAS, or United Technology Research Corporation, outside of Chicago, and they have a lab where we will be doing testing once that's available to us, or once the final rotor is complete and our motor is ready to actually be tested. So we've already completed much of the quality assurance testing, and so we're waiting for the high-speed, high-power facility at United Technologies. And to drive it there, we will be using rotors slightly modified, drives that are slightly modified from the drive from this Boeing 787. And so that test should go to the full megawatt, full 15,000 RPM, with a whole bunch of, we'll learn a whole lot by doing this test once it gets completed. So this is showing a little bit, there'll be a 1 kV DC bus to recirculate the power on there. However, like I said, we'll be using the drives that were designed for the Boeing 787, and those were not designed for 2.5 kilohertz fundamental operation. Their switching frequency is not nearly as high as the drive being developed by the Palawa group, and the way the applied voltage is not nearly as clean of a sine wave. And so concern with that is looking at the harmonics, and the current harmonics there are dramatically higher than the motor was designed for. And so looking at, simulating if we were driving our motor with this inverter without filtering, this is the torque that would be developed. And you don't need to know a whole lot about motors to know that that does not look good. You do not want anything near that much torque. And in fact, at one point, at a few points within the cycle, it would be negative torque being generated. That's not a good situation to be in. And so we also thought about how that would impact the losses, and the copper losses, the AC copper losses would be dramatically higher. And the losses in the permanent magnets also would be dramatically higher than we planned for. And so this is not an entirely resolved issue at this point, but we'll certainly be using significant output filtering will be required. Exact details there haven't yet been nailed down, but there'll be output filtering that's required in order to make this behave appropriately, make it behave reasonably. So conclusion, we've done a lot of work in the past year, and we're getting very close to having the motor actually built and ready to test. Within the next few weeks, we should get initial results from that home-built, much smaller rotor, and within a few months, we should start getting results with the full-size motor. And this hopefully will eventually help lead to electrified aircraft. This is a Stark-able concept from NASA. And yeah, so that's what we're working towards. And thank you for listening. Happy to take any comments or questions. Thoughts? Yeah.
You said United Technologies was right out of Chicago.
Mm-hmm.
You talking Rockford?
Yeah, it's a ways outside of Chicago.
That's the old Sunstrand.
Mm-hmm.
How often do you go there?
Not yet.
Not yet.
Yeah, we.
Old student, an old alum of ours who works there.
Oh, okay.
Worked on the 787 and all the ones before that.
Mm-hmm.
Name's Eric Cunningham.
Eric Cunningham. Okay.
His brother's the one that drowned in Cancun.
Oh.
There's an award. There's an award for somebody in the shop.
Mm-hmm.
His name was David. But Eric still works in Sunstrand. Does motor design. So if you got any problems,
We can talk to him.
I'll give you his email.
Cool. Yeah, we've had a couple meetings starting to get that going. Funding for testing took some work, but at this point, I think we have it set up, and we're starting to work on figuring out the details of how the testing is going to work and stuff.
We'd
So.
love to see this.
Yeah, we'll have to get in contact.
Can you have him as a consultant or something?
Potentially, I don't know. I'm not the one that makes all the decisions, but we should definitely talk to him.
Okay.
And if he works there.
I'll give you his contact.
Yeah, awesome. Yeah.
What's the full-size motor expected to be? How big is it?
How big? The diameter is about 13 inches, so around here, and the active length is 9.5. And
That's a 1 megawatt output.
yeah. So one of the major thrusts of the project is high specific power, and the target is 13 kilowatts per kilogram, which is a lot higher than most. I mean, a regular industrial induction machine could be well under 1 kilowatt per kilogram, and hybrid electric vehicle ones would be in the range of, don't quote me on this, 4 or 5, I think. Melody, do you have a better answer than that? 2 or 3? Okay. Yeah. So our target specific power is much higher than any production things. You can come look at the rotor afterwards if you want. Or the stator, I mean. The rotor is being manufactured. Yeah.
I wasn't clear, how are you going to address the harmonics problem in your drive?
There'll be output filtering.
You're going to design the filter?
Melody looks like she has an answer.
I think you test or Shola also determined this along with you test that we're going to put like big inductor, passive inductor along with the drive.
Mhm.
So we'll figure out
So those waveforms actually is obtained from a setup with filters, but apparently those filters are not big enough, so we're going to put more.
And part of the challenge with our motor is that it's a very, very low inductance. And so most drives rely on the inductance of the motor to smooth out the current waveform so they can provide some distortion in the voltage and the current will be smooth. And our motor just doesn't have very much inductance, so it doesn't self-filter. Yeah.
Will the motor be dyne tested at the UTAS facility, or are you simulating loading?
We need to, that's not fully determined exactly what the tests will look like, but there'll be some amount of testing that they'll drive our motor and then have a probably resistive load for the motor, and then also plan to operate it in as a motor that they'll have some kind of dyno to provide torque. So both directions, and details yet to be absolutely determined. Yeah.
Why didn't you go to Purdue?
I did for undergrad.
Okay. So you've been on Northwestern Avenue.
Uh-huh. Lots.
Fair enough.
Anything else? Cool. Thank you.
Right on time.
Yeah.